Hello, and welcome back to this again really interesting session. And we start with Jacob Foster, professor of sociology at UCLA. Actually, he's a computational sociologist interested in the birth, life, and death of ideas. I mean, how cool is that? Uh, so this involves the social production of collective intelligence and the evolutionary dynamics of ideas. So Professor Foster is a pioneer in the field of meta-knowledge and the science of science. He wrote a number of very influential papers where they showed how to use large amount of scientific papers to extract some exciting insight on the collective scale of science and potentially actually how to improve science in that way. Those works have inspired many people, and definitely including me. And basically, the competition that we have here can be seen in a way as a result of Professor Foster's pioneering early work. So today he will work about science and the social production of collective intelligence or unintelligence. And I'm very much looking forward to that.
Thank you so much, Mario. Thank you for the really kind words. Thanks so much to all of you for the wonderful work, and thanks to Mario and the other folks who organized this amazing competition and invited me to speak here today. I have to say, even as someone who has written papers about the predictability of scientific networks, I was really astonished at just how remarkably predictable the unfolding of this particular network was, given how little information you all were given. Really, just structural information was enough to get these really impressive predictability results. And so what I want to suggest to you today and encourage you to think about is that prediction is the first step. But insofar as we want to change the way science evolves or change the way we do science, we need an understanding of what's driving these predictable dynamics. And that means having a clearer image of how science and scientists work. Now, the old public image of science, imagine that scientists were produced by scientists who were solitary, disinterested seekers of truth, or maybe a collection of iconoclastic geniuses. But these pictures left out a big part of the story, and that opened the door to other images, like the scientist as a figure who is corrupted by social or cultural forces beyond his control. And there's a partial truth to that idea as well. But what I want to talk to you about today is a different way of thinking about science and scientists, one that draws on both the new sociology of science, the field sometimes called the science of science, as well as the field of complex systems. And this is the view that emerges when we turn the lens of science upon itself and try to understand science as we would try to understand any naturally occurring complex system. And my perspective is really to think of scientists like these ants. So this ant has limited cognitive capacity and behaviors, but by interacting with other ants, with the pheromone trails they leave behind, with their collectively built environment, she and her sisters can build and do marvelous things. So we shouldn't think of scientists as intrinsically special. We are all just ordinary humans who are embedded in special social and technical contexts, who draw on certain special interaction rules, and who are equipped by certain training procedures. Because of all of those things, we too can do amazing things. The story we should be telling ourselves about science is that science is a complex socio-technical system for collective discovery and exploration, for collective knowledge making, where by complex system, as I'm sure you all know, I just mean a system of heterogeneous parts that strongly interact and exhibit emergent behavior that can be hard to predict. Fundamentally, I want to challenge the idea that many, especially natural scientists, have, that the social parts of science are the bad parts of science, and that if we could just eliminate those, science would be better. And instead, the story I want to tell you is one in which the sociality of science is essential to its successful operation, but just as constitutive of its failures. It produces both our collective intelligence in the scientific enterprise and moments of collective unintelligence. So by saying the social production of collective intelligence, what I mean is that science is an institution, a social arrangement that produces people, things, and interactions that allow collective knowledge to be created. This is an integrated and relational view of science that puts it in the context of the larger emergence of intelligences across the natural and made worlds. On my view, science is solving an information processing problem, a learning problem. So how can we think about science as this kind of collective learning, this collective computation? Well, first, drawing on some examples from my earlier work on biomedicine, particularly biomedicine is viewed through the lens of chemicals and molecules and so forth. I'm going to draw out some of the core algorithms and distributed protocols that allow scientists to become a collectively intelligent, but do that in a way that respects the hardware of science. In other words, the humans that are actually doing the science. I'm going to address from this collective computation viewpoint one problem, how to organize scientific attention, where I'll mention some perils that can emerge from the ways in which attention is organized, and then spend a little bit of time talking about the formal analysis of scientific institutions, in which I'm going to suggest that if science really is a complex system for learning about the world through the social production of collective intelligence, we need to think really carefully about the policy levers that we can pull on and adjust about the intelligent design of this cultural technology. And then I'll kind of conclude with, if there's time, a very speculative discussion of some of the consequences of artificial intelligence for the evolution of science. Okay, so organizing attention, or another way of thinking of that is, how do scientists choose what to know? Questions, of course, are asked in a rich social and technical ecology. And I'm going to tell you about a paper that came out a few years ago that I wrote with James Evans and Andrei Reshevsky in American Sociological Review. So what affects where an exemplary scientist directs her research attention? Of course, her past interests are important, her training, and these are, of course, the results of social processes themselves, but she also attends to her reputation or her standing in the eyes of her colleagues, her standing in the scientific field, to use the language of the French sociologist Pierre Bourdieu. That reputation is part of what allows her to make further research claims and have them be taken seriously. So the dynamic is, a scientist makes a research claim. Based on that claim and its reception by other scientists, she experiences some return in scientific capital, which might move her up in this space of reputation. Now, what I want to underline is that caring about this sort of thing is necessary, even if this scientist is truly, purely motivated by seeking the truth. Why? Because in order to continue in this occupation where she seeks the truth, she has to stay in the game, so to speak, and playing the game is part of the preconditions of staying in the game. And what I want to argue is that science leverages, tunes, and refines fundamental aspects of the human hardware, our human tendencies, which might be learned, might be culturally produced, and which manifest in many different fields, those tendencies being to attend to status and to attend to others' choices. And that these two features, their exploitation by science as an institution, helps to organize scientific attention. So one of the big distinctions we might make in the space of possible research claims is between moves that involve further clustering attention, following the herd, following tradition, and moves that strike out into new territory, these sort of pirate moves, right? One is predictable, it's productive, it's a bit boring. The other is risky, but exciting. And often in our literature in the sociology of science, we talk about these as the dichotomy between tradition and innovation. These are the terms Thomas Kuhn used, and folks have used various versions of these terms to talk about this basic dichotomy. In my own work, what we've often done is to do something very much like the trick that produced the dynamic network data you all worked with. We took millions of documents that were time ordered and turned them into evolving networks of chemical knowledge, where, for example, if documents A, B, and C have a bunch of different chemical entities in them represented by these little balls, we can turn that into a sequence of networks showing how those knowledge about those chemicals evolves over time. And the first major takeaway from this early work was that a huge amount of tradition occurs. There's a huge amount of herd following. So attention is very, very organized. And in fact, this basic organization of attention, where the vast majority of contributions that are made to this network are kind of preserving tradition, has been stable for more than 2 decades. Now, this stability is even more surprising because the pasture, the space in which possible combinations exist, has gotten vastly bigger. There are many, many opportunities to make new connections as the network has grown, but biomedical scientists are remaining clustered in a very safe little corner. And in fact, there seems to be a powerful herding heuristic at play, something that's in tension with a propensity to strike out occasionally for the new. In this paper, we develop a simple probabilistic generative model to measure the strength of these focusing processes that train attention on tradition. But we want to explain that. What helps to shape and sustain these dispositions? How are they socially produced? Well, training produces them, but also this basic picture of attending to your status in the field. Consider 2 mechanisms for status. One is citations, the usual currency that we use to sort of measure folks' impact. And here I can't avoid pointing out that caring about citations is itself a product of the scientific institution. Part of what I joke to my students, that part of what graduate school does is take someone who doesn't care at all about what journals they're publishing and so forth, and turns them into someone who, as surveyed economists say, would sacrifice part of their thumb past the joint in order to publish in the top journal in their field, in this case, American Economic Review. This is a paper in Economic Inquiry. You can see the citations here. So the scientific institution makes people care about these particular measures of status. It takes a general human concern for status and translates it into these very particular measures. And indeed, we see that papers that are innovative are rewarded more in terms of citations. So making new contributions is more valued. But at the same time, you can ask, is innovation a rational way to obtain citations? I mean, remember that striking out on your own does engage some risk. So you can ask yourself the question, how much riskier is innovation than tradition? Do you think it's like twice as risky, where risk just means like you put a bunch of work in and the paper never sees the light of day? It's never published, no one ever cites it, etc. Do you think it's twice as risky, 10 times as risky? It turns out that the reward, the extra reward for innovating, is so small that to be indifferent between making a tradition move and an innovation move, innovation is only between 24 and 35% more risky than tradition, depending upon whether you're talking about making new connections or adding entirely new entities to the field in the first place. But as we all know, trying something new, combining, weightlifting technology and telephone technology, is much more likely to fail than this indifference would suggest. So if we only cared about accumulating citations, tradition is definitely the best strategy to pursue. But if we look at big rewards, winning major scientific prizes. And in this paper, we considered 137 different ones, including some super elite ones like the Nobel Prize and similar things, as well as papers receiving that very high tier of citations. We see that highly rewarded research output does indeed display more of these risk-taking innovation moves that in the long run establish new traditions. So the lesson of this paper is that under current institutional arrangements, a herding heuristic is good for accumulating citations. That's a very valid individual move under the current structure of science. And that heuristic helps to organize sustained scientific attention around tradition. But at the same time, it's in tension with another heuristic, imitating successful people, Nobel Prize winners and so forth, which is again institutionally sustained by these outsized rewards that adhere to innovation. It's baked in by scientific pedagogy. We all read about the great figures in our field, and it's adapted to longer run opportunities to achieve long-lasting recognition. So what I want to point out here is that on the one hand, science as a kind of distributed algorithm for organizing attention is using basic affordances of the hardware, human striving for recognition and status, to implement this collective discovery algorithm. And this is one of the basic level lessons of work by folks like David Marr. Hardware affects the kind of algorithm that can be used to solve a particular computational problem. But these kinds of little limiting processes can add up and produce collective unintelligent consequences, like getting stuck. So this was something we found in a paper that came out at about the same time in PNAS, where once again, we allow scientists to attend to the importance, in addition to using the same molecular network, scientists' choice processes are affected now by the importance of the molecule as measured by its degree. In other words, the previous choices other scientists have made, as well as the kind of cognitive distance between them measured by network distance. So we write down this complicated generative model, learn the parameters from the data, and the basic thing that we find is that the modal strategy that generates the observed network is conservative. It's to take an important chemical and connect it to a somewhat less important chemical, ideally quite close together in the network. So we know from what I told you before that this kind of local discovery algorithm is reasonably rational for the scientist herself, given a proper understanding of the institution that she's embedded in. But what about collective discovery? Is this kind of distributed algorithm, which is reasonable for scientists, reasonable for science as a whole, or does it impose kind of collective limits on the growth of knowledge? In order to answer that question, we simulated the exploration of a network over and over again and changed the discovery algorithm to see if we could do better than this one that we learned from the data. This is kind of like taking the tape of scientific history and running it over and over again with different scientific institutions. And what we find here, efficiency on the y-axis is measured by the number of basically experiments you'd have to do to discover a certain percentage of the network. The modal strategy, the one we learned, labeled Medline here, is highly efficient for discovering initial islands of knowledge. It's quite rational for the initial exploration of an area. But later on, when we're trying to fill out our full understanding of the scientific network, it becomes quite inefficient. And you can see we actually made like planar networks. You could visualize this process of creating islands of knowledge. Now, in playing the tape of scientific history over and over again with different institutions, we found that there are other more risk-taking strategies that can do much better, but these would be hard to implement on existing hardware, that is, human scientists embedded in current institutions. These more efficient strategies tend to rely on things like combinatorial exploitation, like taking important things, combining them regardless of how far apart they are, or just taking far apart things and selectively combining those. They engage considerable risk for the individual scientist. And because they lead to a lot of failure, they may also be more challenging to get society to accept. So this is showing a kind of soft, collectively produced limit to the growth of knowledge. We can change it by changing institutions. For example, by providing incentives for more radical research behavior. And there are ways, interesting ways to do this. The Howard Hughes Medical Institute has a program that focuses on funding people rather than projects, which kind of frees folks up to take more risk. The Gates Foundation pioneered this grand challenges approach. Andrew Sarrazin was the program officer at the time. That approach explicitly selects proposals on the basis of their potential impact and innovation with a peer review process called championing, where basically it tries to work against the overall conservative tendencies of peer review and especially panel peer review processes. But another interesting institutional response, and I think you're seeing more and more of this with the open science movement, with pre-registration, is to change how we respond to failure. Right now, the dominant tendency has been, if something's failed, it gets thrown out. It never sees the light of day. But this may itself have unintended consequences. If we adopt a regime where research is more coordinated, where, for example, each experiment is performed once and the findings are reported, that can make research much more efficient. So under that regime, we again did this sort of experimentation, playing the tape of history many times under these different institutions, as well as doing some analytic solutions in this case. And we found that coordinating research in this way can indeed make even the basic conservative medline strategy quite a bit more efficient. So the bottom line here is that collective intelligence, human collective intelligence, as an output of our institutions, also needs to be built for change. And changes in the rules for change, to cite the pioneering computer scientist Oliver Selfridge. These limits can be broken by institutional change, but institutional change and institutional design raise real perils of unintended consequences. And I want to tell you an empirical story first about those unintended consequences, and then I want to tell you, describe a sort of theoretical model that helps us think a little bit more about these cases. The empirical case is from a very recent paper that just appeared in NeurIPS, this 2021 NeurIPS in the data sets and benchmark tracks. It's with my student, Bernie Koch, and two collaborators from Google's AI ethics team, Emily Denton and Alex Hanna. You can find the paper in Open Review. And this paper takes up the topic of benchmarking in machine learning research. Benchmarking is familiar to all of you since we all just participated in a benchmarking exercise, as you can see here from one of the benchmarking tables I took from a previous talk. And this practice was introduced decades ago by funders as a way to kind of better measure progress in AI research. It was an institutional intervention meant to deal with some concerns about the efficiency of scientific funding. And it has real advantages. It coordinates scientists around problems. You all work on a particular benchmark formulated through a benchmark data set and a set of performance metrics. It standardizes and makes more interpretable comparison across algorithms. In some ways, because at the end of the day, it reduces everything to this very simple question of how do you do on these metrics on this common data set, it reduces the need to develop an elaborate theoretical apparatus, even for peer review, and allows folks from outside a field to break in as long as they can perform on these benchmarks. Taken together, this has allowed machine learning to make really rapid progress. But it has downsides too. The most common one voiced within the community has to do with overfitting of architectures to data sets. So in other words, if you're working on the same data sets over and over and over again, you don't just have the normal overfitting problem, you have kind of a model-wide overfitting problem where you're over-specializing to features of those specific data sets. It also means that participants don't need to think as deeply or have as nuanced an understanding of the task. And you can get poor alignment between the benchmark and the data generating processes involved in the real world task. So overall, this means scientific progress can be distorted because we may not be as far along as we think. Unintended social harms can be produced because there's a kind of breakdown between how models perform on a benchmark and how they perform in the real world. This is something that, for example, facial recognition really suffers from, and there's been a lot of work within the field by folks like Timnit Gebru and Joy Bologna demonstrating this problem with the representativeness of benchmarking data sets compared to the real world cases. And it can waste time and money by chasing soda performance on benchmarks that are really pretty decoupled from the real world problems we want to solve. So to tackle this question empirically, we drew on this data set called Papers with Code. It's a repository of papers, the benchmarks they use, the code that they use in some cases. It has an ontology of tasks that's created by the community. Papers are annotated through a combination of crowdsourced and algorithmic annotations. And we did a bunch of cleaning to work with these data that are described at length in a data sheet, another institutional intervention that more and more folks are trying to follow. So I want to think about, imagine a machine learning, okay, actually this is a poorly chosen, let's have a better image. A machine learning researcher is trying to decide what benchmark data set to use. And if you think through the cost-benefit calculus she faces, there are strong pressures to align with popular benchmarks, rather than less popular ones that are maybe slightly closer to the real-world task, or even more so to adopt the costly exercise of creating your own task. So thinking in this way suggests three questions. How concentrated is benchmark usage in machine learning? In other words, if we look across all of the different benchmark data sets that could be used for a particular task, how concentrated is attention on a very small number of tasks? Where do the benchmarks come from? Are they being made within the task, or are they being imported from the outside? And what organizations are creating widely used benchmarks? And what we find first is that tasks have become more concentrated on fewer data sets over time. We use something called the Gini index, which is maybe familiar to all of you as a measure of economic inequality. And we find, I mean, in part because time trends could be confounded with various aspects of tasks, like how old it is or how big it is. The panel at the top shows basically like predicted Gini controlling for a whole bunch of features in beta regression models. And what you see here is that there are significant trends in increased concentration for the full data set, for computer vision tasks, which are shown in purple, for method tasks. These are things like few-shot learning or AutoML. The only group of tasks that doesn't show this increasing concentration trend is NLP, which, depending upon the model specification, can actually be somewhat decreasing in concentration. And this really interestingly has to do with some institutional practices within NLP research that really support and incentivize the creation of new data sets. So creating and importing, okay? So we find that indeed tasks create more unique data sets that they import, but most tasks use, and note the difference between what are you making versus what are you using, use imported data sets more, again, except NLP. We don't find any significant evidence for time trends in this creation and adoption business. In part, that's because the data are very noisy. And then the last question you might ask is, well, who's making these super popular data sets? We link data sets to institutions using Microsoft Academic Graph, and what we find is that there are 12 organizations that are responsible for more than 50% of data set usages in machine learning research. The blue dots here are corporate organizations, orange dots are nonprofits, mostly universities. The size indicates total usages across 442 different dataset introducing organizations. 12 elite ones account for more than 50% of usages. The Gini here is huge, greater than 0.8. Just to give you a sense of perspective, the country with the highest level of economic inequality measured by Gini is in the 6.6 range. It's like 0.65. So this is much more unequal than the most unequal country in terms of wealth inequality. So, I mean, what are the takeaways from this? Tasks are using fewer and fewer benchmarks across machine learning research. Task-specific benchmarks are being created, but they're being used at lower rates. And a handful of elite institutions are creating the benchmarks that actually get used. So this has real implications for institutional design. Something has gone wrong with the original intent of trying to use benchmarking to make it easier to measure progress. Dataset reuse makes benchmarking valid, but excess concentration can cause, we don't show that it does, but it can cause epistemic distortion, social harms, and research waste because benchmarks can drift from real-world tasks and architectures can overfit popular benchmarks. This rich gets richer dynamic allows a few institutions or organizations to shape the research agenda of the field, and making good benchmarks costs money. It should be supported, and researchers need to be incentivized to use appropriate rather than merely popular benchmarks. Okay, so in the remaining 4 minutes, I want to quickly tell you about some formal modeling work that tries to get at another peril of institution design. And this is work that we call the game theory of science with Carl Bergstrom and Darcy Song. You can read this paper, Why Scientists Chase Big Problems, for a kind of exposition of this. The basic mental model here is the one that I've been describing. Scientists caring about the consequences in terms of status or reputation in the research claims that they make. So given they care about these things, how do the incentives created by contemporary scientific institutions lead scientists to allocate research effort across problems? Can we model this? The case we wanted to focus on was the case of big problems, where something like the Lamb shift, an unanticipated difference in the energy levels of a hydrogen atom that kind of is measured and then shapes the direction of a field, in this case, leading to the development of quantum electrodynamics. When those occur, these problems that are well-defined in scope, widely agreed to be important, more rewarding in terms of scientific reward than day-to-day work, but not just a grind. It's unclear how to solve them. May be useful to society, may not be immediately, but importantly, pull scientists away from other ongoing research. What shapes that decision-making calculus? So the model we develop is something called a credit race game, where you imagine having these N scientists. They have their kind of normal work that they can do, and then this big problem pops up, and they can choose to work on it, or they can choose to keep working on their outside option. All scientists start at the same time. The first to solve the problem gets the credit. Everybody else gets 0. And we assume scientists want to maximize their credit, but vary in the amount of scientific capital they bring to bear on the problem. This is basically what affects how quickly they can solve the problem. It also affects the rate at which their outside options pay off in credit. So here's the model setup. Scientists who pursue the focal problem pay some startup cost. Their instantaneous probability of solution is proportional to their scientific capital and inversely proportional to the difficulty of the problem. So the time to solution given some group of scientists working on it is distributed in this way. So the probability that a particular scientist wins the race is just how much of the total scientific capital thrown at the problem belongs to her. And the solver gets some payoff V, everyone else gets no payoff. These types of models are often used to model what are called insight problems. You need some insight which just kind of suddenly arrives. So the payoff to scientists who pursue the problem is built as follows. It's the reward times the chance of winning, less the opportunity cost, times the expected duration, and then the cost of entry. What we find is that the individual with highest scientific capital pursue the individuals with scientific capital pursue the problem, and then everybody else opts out. This is not particularly shocking. But what if we change the institution so people can publish partial results? In other words, the green guy might solve stage 1, publish that result. Everyone can start at stage 1 now. Purple gets to stage 2. She chooses not to publish, makes it to stage 3, publishes both of those, solves the problem. What we find, and this is a familiar institution, this is how science works, is that when this institution is present, scientists will publish intermediate results under very general conditions, but it's not always a good thing. You might think, look, it's always good to be able to reveal partial results. This allows us to stand on the shoulder of giants. What we find is that allowing partial progress sharing does not necessarily accelerate the rate of solution. This hasn't showed up in other models because those models assume scientists are forced to participate. If you hold the set of participants constant, partial progress sharing is great. It does accelerate the solution, but participating is a strategic decision. The choice of rules influences who opts in, who opts out, and that institution can allow scientists to drop out of hard stages. There's some very interesting experimental work that we didn't know about when we built these models that essentially confirms this prediction and demonstrates that our mental models can be wrong. So I hope this has convinced you that understanding science is a really interesting, hard, and challenging problem, and that changing the way science works without deeply understanding aspects of its function as a process that socially produces collective intelligence can lead to deleterious unintended consequences. So I'll stop here to leave time for questions. Thank the folks who funded various parts of this work, and thank you all for your organized attention.
Thank you very much. This was really, really interesting, thought-provoking, everything. Yes. I see a number of questions. I also have many more questions. So maybe let's start with one from Michael Kopp. Amazing talk, Jacob, on the benchmark practices cons. Is the second point given really a con? I think the second point was that
that they don't have nuanced understanding of the
right.
Yeah, so I mean, this, I would say it cuts both ways in some sense, right? On the one hand, in some ways, the part of the pro slide where I said, oh, you don't need as much theory, you can just kind of like participate and jump in, I would say that's the positive side. The negative side of that is that particularly in the version of benchmarking where everything is reduced to performance on one particular metric that may poorly capture what it really means to do well on that task. And the fact that in lots of, because in some ways we're engaging in benchmarking among other reasons to, give folks who might want to use these algorithms to deploy them in the real world in various use cases, to deploy them in science, some sense of how they're doing. And this lack of nuanced understanding of the task can lead to a kind of deeper decoupling between the metrics represented in the benchmarking task and the actual real world problem. So that's the version of it, Michael, that I think can lead to, it can be a con, right? Can be a negative side.
Yes, that makes a lot of sense to see that you're actually potentially even more decoupled from the world if you don't even know. Yeah, that's a very good point. Okay, so the next question is by Rahul Siriporapu. Would you say that benchmarks are biased towards well-engineered methods rather than well-researched methods? If yes, how would you reduce this bias when designing the benchmark or evaluating the results?
So I think the contrast you're drawing, Rahul, in terms of well-engineered versus well-researched has to do, with things like kind of detailed technical aspects of implementation, not paying attention necessarily to things like compute time, energy consumption, all of these sorts of dimensions. And I think, I mean, this is something that people in the field of machine learning research have definitely been talking about and been concerned with. Certainly, these energy consumption issues have been a big deal. As there is more of a shift towards like edge computing cases, that kind of consideration becomes important. But it's also been much discussed, right? That this like SOTA chasing, state of the art performance chasing, favors incremental engineering improvements over sort of more profound theoretical advances, because especially if it becomes kind of criterial for publication to achieve SOTA performance on some benchmark, you may have a something that is a kind of profound theoretical advance that has a hard time finding a home in a top venue because in its initial version, it will take time to kind of build it up to a place where it achieves state-of-the-art performance, or maybe does state-of-the-art across a larger ensemble of tasks or better representations of the task. So reducing this bias, I think one of the major changes that can be made is just having a more multi-dimensional evaluation of performance. Rather, like the more that you focus on best performance on this one data set with this one number, that leads to a greater probability of decoupling like the actual optimization problem from the kind of cartoon optimization problem which the benchmark is instantiating.
Yes. Okay. That makes a lot of sense. And Rahul said thanks so much, and also thanks for the brilliant talk and insightful answer. Okay, there's another question by Michael on the reusing of benchmark data sets. So he talks about privacy concerns that make it difficult to gather large parts of interesting data sets. And he asks whether you think this could be one reason. And in computer vision, the data sets need to be extremely large and largely gathered by scraping the internet. Like OpenAI's clip, which cannot be made public, but can be reproduced as a strong law of large numbers kicks in. How do you think about these developments and its impact on science?
Yeah. So this is a very interesting question. I think in some ways, what we're seeing is a kind of crystallization of a configuration of a particular approach, which is deep learning, a general neglect of like really attending to data efficiency in terms of learning, few shot, no shot, those kinds of cases. So that paradigm, which is like just throw more compute at more data, combined with the institutional role played by certain large actors, particularly corporate actors who can access confidential data. So you can sort of see that the kind of data you need is closely aligned with the kind of approach that's being taken scientifically and the kind of institutions that can afford to produce, or even, as Michael points out, have access to these kinds of data. So these three things fit together in a kind of vicious cycle to some extent that further locks in this one paradigm to doing machine learning research. And I would say there are ways to try to break parts of that vicious cycle. I mean, one is moves that are being made by nonprofit funders, by government funders, to make large data sets available. But another, and here I think we should throw this back on ourselves as members of the machine learning community, is trying to think out of that paradigm. I mean, it goes back to some extent to Raul's question about engineering as opposed to kind of theoretical innovation. One way to get out of needing all of these private, confidential, or just large data sets is to try to figure out ways to do better with less data.
Yeah, maybe a last question because it fits so very well. So Michael is a co-founder of this AI Institute here, and he asked, how can we set up actually institute in order to foster innovation? So he calls it very selfish question, but I think that's a perfect question in this
It's
situation.
the most pro-social question because we want to foster innovation. I mean, I think my main message is, that I think the work that is being done in the science of science world, ranging from the more social scientific work to the kind of work, certainly that Mario and other folks have done in terms of like science prediction and so on, that provides us with a really rich set of ideas about levers to explore, things that could be changed. But I think that has to be coupled with trying to really deeply understand the kind of the role of human actors as they're constituted by the scientific training process, which means, that if we want humans that respond, if we want scientists or, AI agents that respond differently to incentives, to problem spaces, and so forth, that's in part a pedagogical problem. But, it also means making careful and to some extent theoretically informed institutional changes, where we build models in advance to try to think through some of the unintended consequences and prevent them from, of course, unintended consequences are never fully preventable. So I'll just say, two things very quickly. One is investment in people over projects is I would say a very robust, like good strategy, because it changes the calculus for individuals around risk. It allows them to adopt, if their funding, their tenure, promotion, et cetera, depends very heavily on the success of particular projects, that naturally incents them to adopt more conservative, easier to publish them. The second is to think about the ways that review processes penalize innovation. And anything where you have a bunch of people needing to fully agree on something for a large reward to be distributed naturally penalizes things that are unusual because someone will find a problem with it. And so these like champion processes where some people can be very excited and that's enough to make a risky bet seem to be very effective. So in general, I think the kinds of things that institutes tend to do, making long run investments on people in the way that, a lot of the corporate research institutes used to do in the sort of heyday, that is a very good overall approach that allows a portfolio of research directions to be pursued. But happy to talk further and follow up with all of you. But this, yeah.
So there are many additional question seems coming in just right now also, and I also have more questions. We are unfortunately already over time. Okay, thank you so much for
Thank
this
you so much.
really cool talk. Thanks.